All right. Are there any questions? Yeah. Explain, meaning what? Could I go through what? I don't have the homework one with me here, right? But but yeah. So what do you need explanation on that? Okay, I mean I'm just a little bit surprised. Right. Yeah. Yeah, you'll do the rank sum test, so. Yeah, try doing it because I already covered this in the class, right? I mean, yeah, if you have any problem, let me know. But I mean, yeah, there are numbers given here. You can arrange them in the ascending order of magnitude, do the rank sum test and all that stuff. Is it what? Medical? Oh, yeah. But there should be a file. Yeah, there is a .m file or mat file is there. I sent you 4 files. Right, you guys got the other files too, yeah. It's not that difficult because this homework the undergrads were doing, so I don't think it will be a problem because the undergrad students were doing that homework. So. Yeah, if you have problems, let me know, but I don't have the homework sheet here. There is really nothing to it other than just working it out, because we already covered the things in the class. I discussed the ratio analysis paper and this is just some problems based on that. Not difficult, you know, easy enough so that, it could be given in an undergrad class also. Yeah. All right, any other questions? So today we are going to move on to the topic of classification, right? And in classification, what you're going to try to do is, remember we had that microarray slide, right? And we use the ratio analysis paper to come up with the confidence intervals, and at every spot we have a number 1, 0, -1, depending on whether red is more intense than green, right? Green is more intense than red, or both are about the same. Now the question is, if you observe many cancer samples, right, and you take that pattern, okay, let's say you have two kinds of samples. One is diseased, right, that has cancer. The other one is normal, okay. So if you look at the expression pattern, let's say across a lot of cancerous samples, right, there may be some genes that are, upregulated, in the red versus the green, right. So you want to basically design a classifier so that it will learn from the training samples that you've given it, and then when you give a new sample, right, the red-green pattern on a new sample, it can tell you, right, whether it is diseased tissue or whether it is healthy tissue, right? So that's the idea in classification. And in classification, every time you go to the doctor, okay, it is really a disease classification problem, okay, because, you have the following situation, right? There are many diseases that have overlapping symptoms, right? Let's say disease D1, D2, and so on, okay? So you know the probability of getting the symptoms, right, given the disease, right? Okay. Now, and all that is there in the books, it's there on the internet everywhere, okay? But the problem is when you fall sick, you have symptoms, right? So you got the symptoms, now you want the classification, you want what is the disease, right? Alright? So what is the probability of the disease given the classifications, right? And your doctor is basically working as the classifier, right? So he or she is going to take that, your symptoms, alright, and use the symptoms basically to come up with, a diagnosis for you. Okay, that is a classification problem. And many diseases have got overlapping symptoms, all right? So that's why it's kind of complicated. But this can be done mathematically, all right? And, it makes use of Bayes theorem, right? So if you have, let's say, classes C1, C2, and so on, okay, up to, let's say, n, right? So, and you know that what is the probability of the data, right, which in this case would be the symptoms, given Ci, right, is known, right? And also you know the prior probabilities associated with each of these classes in the population, right? So from that information, right, you're going to calculate basically what is the probability of class CI given the data that you observe, right? So in the case of your doctor, he or she is going to try to determine the most likely disease that you have given your symptoms, right? And to do this, it's just an application of Bayes' theorem. Unfortunately, I cannot write in here because the thing doesn't work. Okay, we found that out the other day, so I'm writing on the board. So probability of CI condition on D is basically the probability of CI intersection D, all right, divided by the probability of D, right? Which, huh? Yeah, which is the same as probability of D given CI times the probability of CI divided by the probability of D. Okay, but this I can write as probability of D given CI, right, times probability of CI, right, and then I can let this summation being taken over 1 to n over all the classes, okay, because this is a partition, right? C1, C2 up to Cn, right, is the entire set. So I can write D as D intersection, right? And this is basic probability stuff, right? You guys have done that all the time, right? So using this formula, I can calculate the probability of the particular disease given the symptoms, right? And that is what is involved in classification. Now the only problem is that if somebody gave you, like I'll assign some homework problems, okay, there I will give you these probabilities, okay, then you can do the problem quite easily. But if somebody doesn't give you these probabilities, all right, you will have to estimate that from the samples, right? So that's the problem here. And the classification problem here is more complicated because in the case of a disease, all right, you probably have a few symptoms, right? Here, you have thousands of genes on the microarray, right? So potentially you could have like 10,000 possible features or 10,000 possible symptoms, okay? So how are you going to figure out from there which are the important symptoms, right? How are you going to, make the number of possible features manageable? Okay, that's another problem. Not only that, these probabilities you have to learn from the data, okay? And you have results that will tell you that if you observe many samples, right, you'll be able to come up with these probabilities, okay? And that's true for most of the diseases. But if you're going to do gene-based classification of cancer, right, potentially, there are thousands of genes on the microarray, right? But the number of samples that you need to learn the classifier or to train it is pretty small, right? Because unless somebody gets cancer, they don't go and voluntarily donate tissue, so that you can do classifier design, right? So that's the problem, right? And that's a challenge here, that things have to be carried out in the small sample scenario, right? Where the sample size is going to be small. All the asymptotic results and all that will not help at all, okay? So this is the brief introductory discussion about classification, and then we'll get into it. So any questions on that? So pattern classification plays an important role in genomic signal processing. For example, cDNA microarrays can provide expression measurements for thousands of genes at once. And a key goal is to perform classification via different expression patterns. It could be between different kinds of cancer, different stages of tumor development, all right? Or you might want to differentiate between healthy tissue, all right, and cancerous tissue. So this requires designing a classifier or a design function which is going to take a vector of gene expression levels as its input, right? Just like the doctor is taking the vector of symptoms as his or her input, right? And output a class label which predicts the class containing the input vector. So in the case of the doctor, it would be the disease, the name of the disease, right? Now classifiers are designed from a sample of expression vectors, right? Because you need training. Even the doctor had to undergo extensive training in a medical college, right? A lot of case studies, then internships and so on, okay? So the classifier will also require training. So, so this is going to involve assessing expression levels from RNA obtained from the different tissues with microarrays, determining the genes whose expression levels can be used as classifier features. Because on a typical microarray slide, you might have 40,000 genes, right? You do not want 40,000 variables, right? 40,000 features to use for classification. So you have to narrow down that number, and then you will have to apply some rule to design the classifier from the sample microarray data, right? And once you've designed the classifier, then you need the guarantees, okay? Just like if you know that there is a doctor here, right, who makes wrong diagnosis, let's say 95% of the time, okay? You're not going to go to that person, right? I mean, so as a classifier, so similarly for a classifier, if the classifier is making too many mistakes, right? Because you learn from one set of samples, right? But then whatever knowledge that you have acquired, that should work on a new sample that's presented to you, right? That's coming from the population. So it's the same thing for the doctor also. The doctor doesn't have to treat you, okay? He or she may have treated a lot of other patients, and based on that, hopefully they'll treat you correctly, right? So you need to be able to get some measure of the goodness of the classifier, right? How good is the classifier? How many mistakes is it making, all right? So things like that you have to be able to quantify, right? And classification theory falls in like traditional pattern recognition, right? And it is only adapted for the purposes of this course, all right, or for the genomic signal processing area, right? Because here you have the constraint of sample size, then feature selection is a big issue, right? So design, performance, evaluation, and application must take this randomness due to both biological and experimental variability, right? Because in the microarrays, all right, we said there were a lot of sources of variation, right? I mean, the intensity of the laser, all right? Then the person that's doing the washing step, right? And so on, okay? Whether things are properly mixed. Now, three critical issues arise in the context of classification. Given a set of features, how does one design a classifier from the sample data which provides good classification over the general population? You are not interested in doing just classification on the training samples, okay? Because if you can do good classification on the training samples, that's not good enough, because you really want to use the classifier to do classification on data that it has not seen as yet, right? Then the second thing is, how do you estimate the error of a design classifier when data are limited, right? Because you want a measure of the goodness of the classifier. Then the third thing is, given a large set of potential features, such as the large number of expression levels provided by each microarray, right? How do you select a set of features as the input to the classifier, right? Because you don't want to design a classifier with 40,000 genes, right? Now, small samples relative to the number of features are ubiquitous in genomic signal processing and impact all three issues. Because typically in the microarrays, you might have like maybe even if you have 100 microarrays, you're lucky, all right? But you might have 20,000 genes, all right? So that's not a large enough sample size. So that's a challenge. Now, classification involves the feature vector X, right, which has got these D components, X1 through XD, on D-dimensional Euclidean space, composed of random variables, which are the features, and then there'll be a binary random variable, all right, that'll determine the class. So binary random variable Y, and a classifier is a function from the feature space to this class label 0Y, right? So the classifier is going to predict the class. So given a feature vector, it is going to spit out a number either 0 or 1, which will serve as a predictor of the class Y, which means that Y is to be predicted by psi of X, right? The value 0, and we are looking at binary classification, right? If you have, ternary classification, you could have 0, 1, 2, 0, 1, 2, 3, and so on. Okay, the same kind of theory goes over, right? So the values 0, 1 of Y are treated as the class labels. Now in this case, the output of the classifier is either 0 or 1, right? And you're trying to predict Y, which is a binary random variable, right? So the error of the classifier is the probability of misclassification, right? So it's the probability that the class that you spit out from the classifier, class label that you spit out, is not the actual class label, right? And you can see that this is going to be the expected mean absolute difference. Why? Because there are only two possibilities here, all right? If you're trying to calculate this expected value of Y minus psi X, all right? Psi is the class label that is coming from the classifier, Y is the actual label, okay? And both of them are either 0 or 1, right? So this difference, all right, this difference can take what values? Y takes the value 0 or 1, psi also, the output of the classifier is 0 or 1. So what are the two values that this difference can take? And you're taking the absolute value, yeah. 1 or 0, all right? So if you're taking the expectation here, it is going to be 0 multiplied by the probability that this quantity is 0, right? Plus 1 times the probability that this quantity is 1, right? So it's going to become 1 times the probability that Y minus psi X in magnitude is 1, which means Y is different from psi X, all right? So that means this is giving you the probability of misclassification, right? And because of the binary nature of this classifier, all right, and the function also, function Y, this quantity is, if you took the square of this, it will not make any difference, right? If you went ahead and squared this error and then took the expectation, right? Two values are 0 and 1. Again, it's same thing, okay? Either 0 or 1, right? So it is also the mean square error. All right, any questions so far? Yeah, some of these things when I was teaching the undergrad version, I had trouble, okay, because they didn't have the background and all that, and they told me that I should mention that 303 should be a prerequisite for that. But for grad students, I think this should be fine. But again, if you have questions, let me know. Now, you are interested in what is called the Bayes classifier, which is the optimal classifier. So an optimal classifier psi sub d is one having minimal error among all binary functions on RT, right? So that it is the minimal mean absolute error predictor of y, right? And psi d, the best classifier, and epsilon d, they are called the Bayes classifier and Bayes error respectively, right? Now, the classification accuracy and thus the error is going to depend on the probability distribution of the feature label pair x and y, right? How the labels are associated with those, how the class labels are associated with the different feature vectors, right? Now we define a number of quantities. The posterior distribution for x is defined by eta x, which is basically the joint density of x and y, right, evaluated at 1, divided by the marginal density of x, right? So that is the posterior distribution of x. Okay, so this is the probability, right, that y is 1 given x, right? Eta x gives the probability that y, the class label is 1 given x equal to little x, right? And this is obvious because the probability that y equal to 1 given x equal to x will be the ratio of their joint density, right, divided by the marginal density of x. Okay, that's what you have here, right? So in this binary setting, eta x is also the conditional expectation of y given x, right? Why? Because see, eta x is the probability y equal to 1 given x equal to x, right? Here this is a binary setting, right? Y can be either 0 or 1, right? So if you are going to find the conditional expectation, it will be 0 multiplied by the probability that y equal to 0 given x, right? Plus 1 multiplied by the probability that y equal to 1 given x, right? And the probability that y equal to 1 given x is basically eta x. So this is also the conditional expectation of y given x. Everybody here familiar with conditional expectations? Okay, good. So there's nothing new in whatever I have talked about. Now, the error of an arbitrary classifier. So let's say you have a classifier psi of x, right? It is going to take the feature vector x. You apply psi to it, you get the class label, right? It will spit out a label 0 or 1. So the error of an arbitrary classifier can be expressed in this form, okay? Why is that, okay? Look, eta x times fx of x. What is this probability here? Yeah, probability of y equal to 1 and x equal to x. Clear, right? I mean, so in this case, when would you be making a mistake? See, you're summing up this probability, right? I mean, if you're looking at the probability of y equal to 1 and capital X equal to little x, right? If you spit out a label 0, right, then you're making a mistake, right? So that's what you need to sum up. So that's why this integral is being taken over all x's for which your classifier is spitting out a class label 0. That means you're making a mistake, right? So that's the first term. Then the other possibility is that, your classifier is saying that psi is 1, right? Whereas in reality it is 0, right? So you have to sum up that probability too, right? The probability that y is 0 and capital X equal to little x. So that's coming from this term. So that's the total error, right? The two different errors, okay, psi equal to 0, y equal to 1, but psi is giving you a value of 0, right? The other case is y equal to 0, right? Whereas psi is giving you a value of 1, okay? So these are the two errors, and you want to minimize this error here because this is the probability of misclassification. Now the class conditional probability of y given x is defined by probability of y equal to 1 conditioned on x, which is eta x, which we already defined before. So as a function of x, probability y equal to 1 conditioned on x is a random variable, right? That's true because you're conditioning on x, okay? So there's randomness with respect to x, right? So it's dependent on the marginal density of x. Now this quantity eta x, right, this is the probability, right? Probability y equal to 1 conditioned on x. So it's going to be a number between 0 and 1, right? So notice here you have eta x, here you have 1 minus eta x, right? So since eta x lies between 0 and 1, right, what do I have to do? If you're trying to minimize So if eta x lies between 0 and 1, okay, half is like the deciding value, right? One of these will be greater than half, the other one will be less than half, right? If eta x is equal to half, then both of them will be equal, right? So you want to minimize this quantity, right? So basically for values where eta of x is, let's say, greater than half, right? Then you will spit out the class label psi equal to 0, right? Because you want to minimize this overall thing, okay? So, pardon me? Yeah, if eta x is less than equal to half, then you should give the class label should be 0, right? So that, because whenever eta x is less than half, you want to get the contribution from here, okay? Whenever eta x is greater than half, you want to get the contribution from here, right? I mean, that's how you would minimize this sum, right? So the classifier that you end up getting is that, or the best classifier, the base classifier, it should spit out a class level 0 if eta x is less than or equal to half, and it should spit out a class label 1 if eta x is greater than half, right? That will make sure that this whole function here is minimized, okay? Because I know that eta x lies between 0 and 1, right? So 1 minus eta x will also lie between 0 and 1, right? Whenever this guy is smaller, okay, I want the corresponding x to come into this integral, right? Whenever eta x is less than half, right? Whenever 1 minus eta x is less than half, which means eta x is greater than half, right? I want the corresponding x to get into this integral, okay? So because of that, I will get this as my classifier. And this makes sense, okay, because it makes intuitive sense, because if the probability that y equal to 1 condition on x is less than or equal to half, right? That means the probability of y equal to a 0 condition on x will be greater than half. So probability of y being 0 condition on x is more likely, right? So I will make a declaration of 0, right? The classifier should say 0, and in the other case it should say 1. Okay. Any questions? Is that clear to everybody? Yes, sir. Go ahead.
What do you want to do with this psi d?
No, psi d is the best classifier, okay? It is the classifier, right? I'm choosing a particular psi, okay? Psi d is the best classifier. It is the classifier that is going to minimize this misclassification error probability, right? And the way I'm choosing it is because here the thing that I have to choose is just the psi, okay? I'm going to choose the psi in such a way that all the values of x for which eta x is less than half, alright, they will come into this integral. And the way I can do that is by making sure that for all these values of x, psi x is 0. Okay. And here I want all the values of x for which eta x is greater than half, I want them to come into this integral, right? And the way I can do that is by choosing psi such that I'll get psi x equal to 1, right? For all the values of x over here, where this guy is smaller. 1 minus eta x is basically less than or equal to eta x.
How we can choose this eta?
Yes. We'll get to that, yeah. For now, let's assume that somebody is giving you the eta, okay? But the problem is you don't have the eta. We are getting to that in a few minutes, okay? But yeah, so here I'm assuming that I have the eta, okay? If I have the eta, then I can choose this as my base classifier, as the best possible classifier, which is going to minimize the probability of misclassification, right? All right. Yeah, we'll talk about how you're going to choose, yeah. That's the hard part because, that's not given to you, okay? These probabilities are not given to you. That's what is going to make things difficult, okay? But before that, let's say you have chosen this optimal classifier, right, which is the base classifier. So now you can actually replace psi by psi d, right? And you can write down the formula for the error of the best classifier, okay, which is called the Bayes error. So if you just apply the classifier that we have designed, so it follows from the above two equation that the Bayes error is given by, because this is going to be the set of all x. See, psi d of x equal to 0, right, is the set of all x where eta x is less than or equal to half, right? So this thing I can replace by the set of all x's such that eta x is less than or equal to half. This one I can replace by the set of all x's such that eta x is greater than half, right? So, and that will give me the the expression, the integral expression for the Bayes error. So it follows from the above two equations that the Bayes error is given by this expression. Okay. Now the problem with the Bayes classifier is that we typically do not know the class conditional probabilities. That's what you were talking about, right? And therefore we must design a classifier from sample data. Right? An obvious approach would be to go and estimate the conditional probabilities from data, but often we do not have sufficient data to obtain good estimates. Right? And moreover, good classifiers can also be obtained even when we lack sufficient data for carrying out density estimation. Right? So let's see how we do all of those things. So next we will talk about designing a classifier based on sample data, right? Because if somebody came and gave you those probabilities, it's just like this disease, okay? Somebody came and gave you these numbers, it's very easy to work out a textbook example. That's what you're going to do in those homeworks that I will assign, okay? It's a textbook example, but in the real world, that information is not there, okay? So you have to build that up from samples that you see. So design of a classifier psi sub n. Now the classifier is a function of the sample size n, right? From a random sample Sn of points like this, okay, feature label pairs, right? X1, Y1. X1 is the feature vector, Y1 is the corresponding label. X2, Y2, and so on, okay? So if it's cancer versus normal tissue, okay? So there would be two labels, maybe 0 is cancer and 1 is normal, okay? So corresponding to each feature vector, you will going to know whether if it's training data, you will know whether it's normal or it's cancerous, all right? So design of a classifier from a random sample of vector Sn of vector label pairs drawn from the feature label distribution requires a classification rule that operates on random samples to yield a classifier. A classification rule is a mapping psi sub n which basically takes in the feature vector, the d-dimensional feature vector, right, times cross product with the class label. So the feature vector class label, right, and it is going to spit out f. So it's going to spit out this function, right? That'll give you a function f where f is the family of 0, 1 valued functions on RT. Okay, because you are looking over binary classes. It can be others. Okay, so you want a function that is going to map it's going to map feature vector, right, and class label, right? So you're observing these samples. So based on these samples, now you got your classifier, right? It is a function of the sample size psi n, okay? And so now if you're given a new sample, right? So given a sample, we obtain a design classifier, which is obtained basically by operating this classifier or this classification rule on the sample that's given to you, the feature label, pair that's given to you, right? Now the Bayes error, epsilon d, which is the minimum error, which is the error of the best classifier, is estimated by the error epsilon n of the classifier that you have designed based on the sample, right? So there is a design cost associated with this, which is epsilon n minus epsilon d, because epsilon d is the error of the best classifier. If you just based it on some samples, right, your error will be larger, right? So there will be some design cost, okay, because I don't have all those probabilities. I have to estimate stuff from the samples that I get, right? So epsilon n and delta n will be sample dependent random variables, and the design cost is the difference between epsilon n, right, that is the error of the classifier that is designed, and the Bayes classifier. So epsilon n minus epsilon d. So, and again, this is a random variable because epsilon n is a random quantity, right? Because it's coming from the sample, right? See, to get that epsilon n, we basically had to design this classifier psi n, right? So it's a function of that sample size n. So you have to take the expectation. The expected design cost is the expected value of this error, this design cost, delta n, and the expectation being relative to all possible samples. Okay. Now, the expected error of this classifier psi n, you can decompose it into two parts. The expected value of epsilon n is epsilon d, which is a deterministic quantity. Okay, it is the error of the Bayes classifier plus the expected value of delta n. Right. So nothing major here. You just take this, take expectations on both sides, and keep in view the fact that epsilon d is deterministic. Right. So you get this relationship. Now the problem is, see, you have theorems that will tell you that as the sample size becomes very large, right, then this epsilon n is going to converge to epsilon d, right? The delta n will go to 0. But those asymptotic results don't apply here, okay? And the way, the fix around that is, see, the Bayes classifier does not make any assumptions about the structure of the classifier. Is it going to be a linear classifier? Is it going to be nonlinear? Okay. Bayes is the best over all possible classifiers. All right. So if you go and impose some restrictions, like let's say you are going to design only linear classifiers, all right, then you need a lot fewer parameters, and the design of the classifier will require a lot fewer training samples. Okay. It's just like, if you're trying to estimate a function, okay, you know nothing about the form, all right, then you need lots of data. Okay. But on the other hand, if you know if it's a polynomial of order 2 or 3, all right, then you need to just estimate those 2 or 3 coefficients, right? So you can manage with a lot less data. So it's the same idea that will be exploited here. All right, any questions? So the asymptotic properties of a classification rule concern large samples as n goes to infinity, right? And a rule is said to be consistent for a distribution, for a particular distribution of the feature label pair, if this delta n, this design error, goes to 0 in the mean, meaning that the expected value of delta n goes to 0 as n goes to infinity. Now for a consistent classification rule, the expected design cost can be made arbitrarily small for a sufficiently large amount of data. Now since rarely is there a good estimate of the distribution in pattern recognition, right? Rules for which convergence is independent of the distribution are desirable, and a classification rule is said to be universally consistent if delta n is going to go to 0 in the mean, no matter what the distribution of the feature label pair. Okay. Now universal consistency is useful for large samples because as n goes to infinity, the design error goes to 0, right? But it has got very little utility for small samples. And in genomic signal processing, in cancer classification, we are typically dealing with small samples, right? So we don't have much use for these kind of asymptotic results. Now in this chapter, we are going to discuss a few well-known and well-studied classification rules, our intent being to use them to illustrate methodology and issues, right? Now again, I mean, there is a course in pattern recognition that is taught in the spring semester, right, in this department. So if you're interested, you can take that course, okay. There you'll worry about the deeper math questions and things like that, okay. Here, it's more like hand waving and, I'm going to try to give you the big picture because, that's not my area of specialization. And if I'm not mistaken, there's probably a course in computer science also that deals with pattern recognition, So yeah, have you taken that or no? Yeah, so
Similar course is given in information storage and retrieval.
I see.
All the probabilities.
Okay. So yeah, those courses are there, and at least, if you've taken that course, that's fine. If not, you can take it. If you took that course, at least you can see that it's being applied in right now in a hot area, okay? So, I mean, everybody wants to work in hot areas, so this is traditional stuff that is showing up in hot areas, okay? Like you have big data and all these things, okay? So the first classification rule that we'll talk about is the nearest neighbor rule, right? Where basically what you're going to do is, if you have a bunch of points, okay, you want to classify the point, okay, you look at the label of its nearest neighbor, okay, and you just give it the same label as that of its nearest neighbor. So for the basic nearest neighbor or NN rule, psi n is defined for each x in Rd by letting psi n of x take the label of the sample point that is closest to x, right? And for the nearest neighbor, and these are again things that can be proven. Okay, I have not read the proofs, but if you look at the literature on pattern recognition, probably people did these proofs maybe 30, 40, 50 years ago. They're all available. So for the nearest neighbor rule, no matter the distribution of x and y, right, regardless of the feature label distribution, you can show that the expected value of this design error, right, as n goes to infinity is bounded from below by the Bayes error and bounded from above by 2 times the Bayes error, right? And it follows from here that the limit as n goes to infinity, the expected value of the design error is less than or equal to the Bayes error, okay? And this you can do just by using triangle inequality, right? This is bounded between epsilon d and 2 epsilon d. You have the formula for delta n, right? Expected value of delta n. Just use triangle inequality or some variation of that, you will get this, right? So the asymptotic expected cost of design is small if the Bayes error is small. However, this result does not give consistency. This is not telling you that as n goes to infinity, right, that this error is going to become very small. So it's not consistent, right, even when the sample size becomes large. Now more generally, so instead of the nearest neighbor rule, if you take the k nearest neighbor rule, that means you will consider the k nearest neighbors, right, to the point that you're looking at, and you will give it the label of the majority, right? So you'll take an odd number of neighbors. So more generally for the k nearest neighbor rule, k odd, okay, odd so that you can get a majority, right? I mean, if it's even, it's going to be a tie, right? So you have to break the tie. So you take an odd number k. The k points closest to x are selected, and psi n of x, the class label, is defined to be 0 or 1 according to whatever is the majority among the labels of these points, right? Among these k nearest neighbors. If k is equal to 1, then you get back the nearest neighbor rule, right? And for obvious reasons, we will not consider even k, because if you have even k, you have to break ties, okay? Or you may have to break ties. Now the limit of the expected value of this design error, right, epsilon n, as n goes to infinity, can be expressed analytically, and various upper bounds exist, right? And again, if you're hungry for some exercise in mathematics, you can go and look at the literature, try doing those proofs and things like that, okay? Or maybe, who knows, in the pattern recognition course, maybe they might force you to do these things, all right? I don't know, I have not sat in through that class, but it is offered in the spring. Right? So in particular, one bound is that as n goes to infinity, the expected value of the design error is bounded by this, where k is basically the number of nearest neighbors you're considering, so k e to the power of minus half. So this still doesn't give you consistency, right? It doesn't tell you that as n goes to infinity, expected value of delta n goes to 0, right? But it does show that the design cost can get arbitrarily small for sufficiently large k as n goes to infinity, right? So if you have many neighbors, all right, if you're using many nearest neighbor rule, right, you will do better than just using like the nearest neighbor rule or the 3 nearest neighbor rule, right? As you increase the number of neighbors, you probably will do better. And that also makes intuitive sense, right? I mean, you're looking at more people before trying to copy. You're going to do a better job. Assuming that all the people that you're copying from are not generating garbage. Right? So the k nearest neighbor rule is universally consistent if k goes to infinity and k over n goes to 0 as n goes to infinity. Right? And again, I mean, you can make out from the flavor of these statements that these are basically math results. All right? You could look at books or papers on pattern recognition, these things are worked out. Right? Now a classification rule can yield a classifier which makes very few or no errors on the sample data on which it is designed, but performs poorly on the distribution as a whole and therefore on new data to which it is applied. And this situation is made worse by complex classifiers in small samples, right? Because again, I mean, in the genomic signal processing domain, you are stuck with small samples, right? And on top of that, if you design classifiers which are complex, you have trouble, right? Now, if the sample size is dictated by experimental conditions such as cost or the availability of patient RNA for expression microarrays, right? So the sample size will be small in the genomic signal processing applications. Then the only thing you have control over is the complexity of the classifier, right? This design function that you're going to use, okay? You have control over how complex or how simple you're going to keep it. So the situation that we are concerned with is typically referred to as overfitting, right? The basic point is that a classification rule should not cut up the feature space in a manner too complex for the amount of sample data available, right? If you have very little data and you did overfitting, then when you get new data, you're not going to do as good a job, right? So the problem is not necessarily mitigated by applying an error estimation rule to the design classifier to see if it actually performs well. Because when there is only a small amount of data available, the error estimation rules are also very imprecise. And the imprecision tends to be worse for complex classification rules. Hence, a low error estimate is not sufficient to fully overcome our expectation of a large design error when using a complex classifier with a small data set. So if you have a small data set, you should never use a complex classifier. Like you should never use a neural network if you don't have enough data to train it, okay? Because that is a complex classifier. Now, overfitting is illustrated in the following figure, all right? See, here you have a bunch of points, all right, that you're trying to classify. And these are coming from circular class conditional, Gaussian class conditional distributions, right? One is here, right? The base classifier is this vertical line, okay? There's a straight line that will separate them, okay? But let's say you don't know that. So in each of these, that base classifier is shown. So if you're going with 30 samples in the two upper figures, all right, and you design a classifier using, I think, the 3 nearest neighbor rule, all right, you come up with this decision boundary that is shown here. Okay, you can see that because of the small sample size, all right, you have a pretty large error because the optimal boundary is this one. Okay, but you came up with this, right? Same thing here, right? You switch from one sample to another. Now this one is fitting this data. This is overfitting here. This is also overfitting this new data, right? On the other hand, if you have a much larger sample size, you use the same method, right? You got a pretty good approximation, right? I mean, to this line, it's only jutting out a little bit, right? You're doing a lot better. Not only that, when you change the data, you flip the data, you're pretty close, right? It's not like it's from here, it's suddenly come here, right? Do you see that? I mean, so, if the sample size is large, right, then if you have complex classifiers, you're okay, right? But if the sample size is small, you have this danger of overfitting. So overfitting is illustrated in the figure that I just showed you, in which the 3 nearest neighbor rule is applied to 2 equal variance circular Gaussian class conditional distribution. Parts A and B show the 3 nearest neighbor classifier for 2 30-point samples, and parts C and D show the 3 nearest neighbor classifier for the 2 90-point samples. All right. Note the greater overfitting of the data for the 30-point samples, in particular the greater difference in the 2 30-point design classifiers as compared to the difference between the 2 90-point classifiers, and the fact that the latter, that means the one on the larger sample size, the closer they are to the base classifier given by the vertical line. Okay, all that is shown in that figure that we put up a moment ago. So in genomic signal processing, we are stuck with small samples. Okay, so we cannot design complex classifiers because we will have this overfitting problem. Right? It might do well on the training data, but when you give new data for classification, it will do a bad job. Right? So to mitigate this need for large data requirement, we need to use constraint classification rules. Okay, let's not look over all classifiers. Let's give some structure to the classifier. So constraining classifier design means restricting the functions from which a classifier can be chosen to some class C. This leads to trying to find an optimal constraint classifier. So now we are going to look over the optimal over a smaller class. It will make our job easier, but then we have sacrificed some performance because now we are not looking at, we're not trying to approximate the best possible classifier. Right? So let's find an optimal constraint classifier psi C belonging to that class having error epsilon C. Now constraining the classifier can reduce the expected design error, but at the cost of increasing the error of the best possible classifier. Right? Because see, the design error will go down because it's a constraint classifier. So it has probably less variables, less parameters, whatever, so I can design it more easily. Right? So my design error will be smaller. But in order to go from the base classifier to this constraint classifier, I have sacrificed some performance because now I'm looking at the best one in a smaller class. Right? So since the optimization in this class C is over a subclass of classifiers, the error epsilon C of psi C of the constraint classifier, the error epsilon C of the best constraint classifier will typically exceed the base error unless the base classifier happens to be in that class C. Right? And this cost of constraint or cost of approximation we are denoting by delta C. This has nothing to do with the sample size, even before I add one sample, okay? Because I have restricted the structure of the classifier, that is increasing my error, okay? So this is the cost of constraint is given by epsilon sub C minus epsilon D. So this is going to be larger than the base error. The difference is the cost of introducing that constraint. Now a classification rule, right? So now we are designing constraint classifiers. So a classification rule yields a classifier psi NC. Okay, that means it's a classifier that is designed based on samples, all right, from that constraint class with error epsilon of NC, and this error epsilon NC is going to be greater than or equal to epsilon C, all right? That is the error of the constraint class, the best constraint classifier. So epsilon NC will be greater because you're now learning things from samples, all right? And this in turn will be greater than or equal to the error of the base classifier, okay? Because base classifier didn't have any constraints on it. That is the absolute best, okay? That can be done, all right, without any constraints. So the design error for constraint classification, delta NC, all right, is going to be the difference between the error of the design classifier and the error of the best classifier within that constraint class, right? Now for small samples, this can be substantially less. See, remember when we were trying to design the base classifier, right, we had a design error delta n, okay, which was the difference between epsilon n and epsilon d, right? So this can be for small samples. For large samples, you know, if you let n go to infinity, probably you can drive delta n to 0, right? And you can get to the base classifier. But we are working in the domain of small samples. So for small samples, the error, the design error for the constraint classifier may be much smaller than the design error for the base classifier, right? And the error of the design constraint classifier is decomposed as epsilon nc equals epsilon d plus delta c plus delta nc. So because you have the base classifier, right? There will be some error because you put in the constraint, right? And then on top of that, there will be some error because of the design, right? So you can break it up like this. And the expected error of the design classifier from this class C can be decomposed as you take the expectation. So epsilon d is a deterministic quantity. And then you have delta C, right? Again, the deterministic quantity because that is the error cost of approximation, right? Nothing random about it. And then you'll have this error because of the design error for the constraint classifier, right? Now the constraint will be beneficial if and only if the expected value of this guy, right? Of the expected value of the error for the constraint design classifier is less than the expected value of the original classifier, right? Designed based on Bayes rule. Okay. I mean the original classifier that was trying to approximate the Bayes classifier, right? Which means, and you can do the math. You have the expression here, then you have another expression. You can say that the constraint is beneficial if the cost of constraint delta c, right, that you are incurring, right? Delta c is the amount by which the Bayes error is increased. Okay, because when you put that constraint, if that happens to be less than the error, the design error associated with the Bayes classifier, and the difference between the design error associated with the Bayes classifier and the design error associated with the constraint classifier. Right? It's just a question of the math. Put in the terms on both sides, cancel things out, you'll get this relationship. Right? And we can show that quite easily in a picture. I'll do that in a few slides. Right? So if the cost of constraint is less than the decrease in expected design cost, then the expected error of psi n c is less than that of psi n. Right? Now choosing a complex classifier that can tightly fit the data reduces the constraint cost, right? But it increases the expected design error expected value of delta nc. Whereas choosing a simple classifier that does not overfit the data is going to increase the constraint cost, but it is going to decrease the expected design error, right? So in most microarray experiments, the sample size is very small, and the design error is such a problem that you're always going to use simple classifiers because your sample size is small. Okay, you just cannot afford to go with complex classifiers. And the matter can be graphically illustrated, right? And I'm going to get to that picture in a minute. So for some rules, for some classification rules, you can show that the expected value of this design error is non-increasing, right, as a function of n. So meaning that the expected value of delta n plus 1, right, when you add a sample, right, sample of size n plus 1, all right, that is actually less than or equal to the expected value of delta n and so on. Okay, so there is monotonicity. So this means that the expected design error never increases as sample size increase, and it holds for any feature level distribution. Such classification rules are called smart. The nearest neighbor rule is not smart, right? Because there exist distributions. So is it stupid? I don't know. Okay, because there exist distributions. It's like the smart grade. You know, somebody said that smart grade is probably not a good name. You know, there was the grade stupid before. You know, so because there exist distributions for which the expected value of delta n plus 1 is less than or equal to expected value of delta n does not hold for all n, right? So the nearest neighbor rule is not smart because there will be distributions, feature level distributions for which this doesn't hold. Now consider a consistent rule, constraint and distribution for which this relationship holds. So both the design without the constraint, right, that is the approximation of the Bayes classifier has this property, and even the constraint classifier also has this property. That means as n increases, the sample size increases, the error goes down both with and without the constraint. Yeah. Uh-huh. No, it does not. Yeah. That's what it is saying. It may be for some distributions, but not across all distributions. Because if it is going to be smart, all right, if you look at the previous slide, if it is going to be smart, all right, it has to hold for any feature level distribution, right? Can increase, yeah. But k is 1. This is nearest neighbor. Was this k nearest or was it nearest neighbor? This is nearest neighbor. So k is 1 here. Yeah, k. This is nearest neighbor, not k nearest neighbor. So k is 1 here. Anyway, so let me show you the picture because the picture will tell the whole story. All right. So here we are assuming that we have, smart rules. Okay. So the error, the expected value of the error so this is the base classifier, right? Epsilon d. This is the minimum error. It doesn't depend on the sample size, right? It is the lowest possible error. This is the error of the best classifier. Now you try to approximate this, right? Using some samples, right? You're trying to learn that, and you calculate the error, right? The design error, and this design error actually goes down monotonically as the sample size increases. In the limit, this error will match up with the base error. Okay. Now the other scenario is where you have constrained the classifier, so upfront, even before you took any samples, right? You've already lost out something, so the error of the constrained classifier, the best constrained classifier is shown by the dashed line here. Now you go ahead and design the constrained classifier using samples, right? So there's a design error associated with the constraint classifier because of which the expected error will look like this. Right? Again, it asymptotically is going to approach epsilon c. Right? Now, if you are in this region, okay, until you hit this point, okay, then the error of the constraint classifier is lower than the error of the unconstrained classifier. So in this case, you will, if you are operating if your sample size is in this region, right, to the left of this intersection point, then use the constraint. The constraint is beneficial, right? If you are to the right of this point, then here you can see that the base thing is becoming smaller than the other one, right? The design error associated with the base classifier. So here you would not use, the constraint would be detrimental if the sample size was large. And both these rules are smart. That's why you're able to show them as monotonically decreasing like this. Okay. So if n is sufficiently large, then expected value, this is what I showed in the figure. If n is sufficiently small, then this one of the expectations is greater than the other. The point n0 at which the decreasing lines cross is the cutoff. For n greater than n0, the constraint is detrimental. For n less than n0, it is beneficial. Right? And if n is less than n0, then the advantage of the constraint is the difference between the decreasing solid lines. Okay. So the benefit from the constraint is basically this. Right? This stuff here, difference between expected value of epsilon n and expected value of epsilon n c, depending on where the sample size is, the difference between these two lines. Okay, so I will stop here for today. All right, next time I'm going to discuss a few different methods, all right, that are commonly used for classification, right, like linear discriminant analysis and so on, right. And if you take a course on pattern recognition, they will cover those things in a lot more detail. So I just want to build up some working knowledge here. Okay. Okay, let's stop for today.